The title is very long, looks like an abstract already, right? And I apologize to some of you in the audience because I was talking about this topic already at the DD27 in Prague, but I thought it is a quite nice. You have to judge yourself, but it's a good continuation of what Gabriele was talking about. And non-overlapping domain decomposition he did on semi-linear equations, and I would like to introduce stuff on p-parabolic problems. Is there anything I need to do, or? Okay, good. Yes, so the title has to be debated. So why at all do we metric graphs? This is something that did not come up here so far. So graphs appear in many applications. And I show you only one application today is gas networks. But of course, you can also think of the cardiovascular system. You can think of electric networks. It consists of water networks, irrigation systems, and whatnot. So typically you have in engineering, people think of one-dimensional representations of such phenomena, and the one-dimensional representation then leads to graphs. So you have a typical situation, you have, and this is like the building block for any graph, is the multiple junction. Right? This is the novelty somehow for most of you. So instead of just having a domain, which is somehow an open set, or which is a manifold, here you have a domain which is not a manifold, right? So it's a different object mathematically. And the major concern, of course, then is the junction point, right? What happens at a junction? And of course, you can also think of systems like this, where you have planar domains that meet, at a certain thing like this. You can also consider, right? And what this is behind this is what one calls masonry structures, like houses or furniture is all made out of plates or membranes or whatnot. Right? So there's a certain generality in this, and of course you can also think of things like this, where you have in fact domains like this, and then another 3D domain coming in here, so you have somehow this kind of structures, right? And of course this happens to be the case in real systems. So an engineer, if he starts out doing gas, you would think of gas that has turbulent flow, maybe in the neighborhood of valves and compressors. You have the same situation for blood flow, and you may know the work of Alfio Quattroni and his group in Milan, or also in Lausanne in earlier times, where they considered dynamic equations, in particular Navier-Stokes equation, Saint-Venant's equation, or water hammer equations in such networks, right? And you can also think of many other details, where you have have a fat junction. I should call it fat graph or fat junction, and you do all kinds of asymptotic analysis in order to retrieve out of this real 3D domain little 2D domains that come out of this. So this is all in the context of networks. So this is what I call graph, and I call it metric graph because in contrast to graph theory, you just have discrete graphs there. So here you would have just the nodes, right? And you talk about maybe 1, 2, 3, 4, and then you can talk about adjacency matrices or edge to node incidence matrices, etc., etc. But here the edges are intervals. They can be any Jordan curves actually, and also in the higher dimensions you can do that. So you see, and these structures may carry and will carry in the talk partial differential equations, right? In my case now, 1D situation. Now, why do I tell this here in the school for domain decomposition, right? First of all, clear, I mean, one can formulate, and I will do that, optimal control problems. But secondly, the question is, you have seen the talk by Axel Clavon and also Rolf Krause and Victorita Dolian. You see, and also others, I mean, you talk typically about domain decomposition in higher dimensions, right? So 1D, locally 1D. You would think, well, this is a trivial thing numerically, right? And the first slide should give you a little bit on why at all would one think of domain decomposition in space and time in such a situation, right? We talk about, I will show you a picture of large-scale networks, even though in the talk and also in the numerical experiments, and I have to say I'm not a numerical analyst. I do the numerics just for making, you know, evidence, numerical evidence, Stefan.
Yeah.
And for that matter, I will use only standard open software for this, right? And I don't mess around with my own finite element codes or something. In any case, large scale means you have thousands of edges, maybe, right? And for each pipe, you would need space and time discretization, right? And I think Stefan gave a very nice introduction to optimal control, and you see how fast the dimensions can grow, right? And you can go into the millions or billions of variables, even in a locally 1D network. If you also consider maybe what Tomasio was talking about, randomness, so you have to do it repeatedly. And even most demanding, and this is the case in almost all applications, is real-time capability. Right? You need to do this in real time. I mean, the people, I'll show you networks of gas, are communicating, the operators are communicating, they need the information on the entire network in maybe half an hour. Right? And then you get to a situation where you think about reducing, either reducing the model using surrogates or doing domain decomposition or doing domain decomposition. So I believe this is sufficient intuition maybe to say, yes, you can continue talking on domain decomposition of locally one-dimensional stuff. Okay, so here you see the German gas network. I mean, you see on a high hierarchy. I mean, these are large pipes. I'm not talking about the pipes that are sitting in your house, right? And you can imagine similar things in cardiovascular systems. You have large major pipes, the aorta, and then you have these in the fingers, you have these fine capillaries, right? That you do not model at all, right? And you can model this using homogenization, many techniques using surrogates. So these are only larger pipes that are considered by the companies Open Grid Europe, right? And they do the data for the network. You see, the situation is that you have providers. One is now, on holidays. This is Russia, right? And you have customers, and the customers are still the same. You have a forest, so to speak, of interest. So those trees who connect from the providers to the customers, and then you have pipes that interlink these networks, and this makes the thing complicated, right? But this is what you want. You want to optimize the flow from the provider to the customer. These are long-year contracts. It's very complicated, right? It's complicated, the stuff. But in principle, mathematically, you should be able to say, can I use controls, and which controls? Can I use controls to steer the flow through the network to the customer? And the customer wants gas of a particular quality even, right? And now the challenge is in these days to use this network also for hydrogen, right? Because natural gas is running out, and you have to transport hydrogen also in future. This is it's a different problem because you have different pressures and so on and so forth. So what I'm putting here on this, you can even look into this. You can just download the graphs from GASLib and see a little bit what the complexity is. But the data is available. You can use this, it's open. Okay, so what I'm saying here, you have complicated graphs. You can somehow extract simple graphs. And the final idea is to somehow do a decomposition of the whole network into sub-networks, right? But in the talk, it will be very simple, just, tripod. But this is behind all this, right? Okay, so let me start with the mass. So in a gas pipe, you have Euler's gas equation. These are the 1D gas equation without the energy equation, so isothermal thing here, and also without dependence on the slope. So gas pipes have a slope, and the slope enters the dynamics, and this is particularly important if you go with gas pipes over the Alps, which is in fact happening. So you have to be careful about the modeling right at this point, right? So it's extremely important in these applications not to go a very far step at the very beginning in the modeling. I would love to be able to, I could write down what is the system of equations for Euler gas equation on a network, right? I can do this. But I cannot do, at this point, domain decomposition for that, right? I'm not able to do a non-overlapping domain decomposition for the full Euler gas equation on a network. You see, let me also say a word here on domain decomposition. If you have a graph like this, the domain decomposition you do in engineering would be a non-overlapping domain decomposition with respect to the word you used, the substructuring. In fact, I learned this from Destoinder in a paper earlier, right? So you want to decouple at the joints, right? You can, of course, also decouple here, right? And then you are in the Schwarz business, right? You can do overlapping, non-overlapping. You can cut out stars, right? This is what I call cut out a star. And you could consider a star like a brick that you use, like a finite element, and then you decompose into these elements. And we call this recently with Sebastian Pokutau, in fact, was a student, I believe, of Axel Clavon, or was with him, NETI, network tiering and interconnection, instead of FETI. But you see, this doesn't make any sense here. You cannot do an overlapping domain decomposition here, right? And this, in fact, is just a picture that you see also in the Lyons paper. If you have such a thing, no chance, right? So you do have to do this on the multiple nodes. In any case, I'm not able to do it here. Okay, so there is a very nice old, in fact, an old paper. So here I just also show you some sample graph again. You can neglect inertia in these equations and obtain this equation, right? You can do that. This was done by the first engineers that I know is Stoner in 1968. There was a dissertation in the US, he did this. Now, there is an asymptotic analysis where you actually can prove that you can go from, if you do epsilons here and here, that you can actually have asymptotic convergence to this model, right? And this is done by Egger and Herbert Egger and Jan Gieselmann recently. So this is the model we talk about. And in fact, if you have constant states, I mean, P is constant, then this is a constant, and this is then called the so-called Weymouth equation, which is used in optimization. And let me tell you right at the beginning that you can somehow see what is this all about. We have control instruments in gas networks. These are valves, and these are pumps, and these are compressors, right? And all these instruments are nonlinear controls in a pipe. So if you have a pipe, maybe I take this here. we talk about the pressure P and the flux Q, right? And if you have a serial element, so you would have a pressure 1, a pressure 2, and if this is -1, x is 0, and this is x is 1, okay, do you have transmission? The pressure typically is constant, is equal across a serial joint, and also, of course, in principle, the flux is equal, right? But for instance, one boundary condition that people look at is this. So you have P2.
We have a problem with the screen.
Yes, but while I'm writing on the board, maybe somebody can help. I will show you just one. I will show you just one nonlinear control boundary condition, which is extremely simple. The Q is constant across, is continuous across the joint, and compressor here leads to such. I mean, this is already a dramatic, simplification. A compressor is a building as large as CIRM is, maybe, or even larger, right? It's a very complicated thing. But you see, mathematically, if U is 0, U is the control. If U is 0, you have continuity of pressure. And if U is larger compared to Q, then you have a difference of pressures. And you see the control is on the boundary and is highly nonlinear. Highly nonlinear. Another word on controls, right? In engineering or in applications, you never have distributed controls. Never. Right? Because you can never act on the entire system. It's impossible, right? So you always have control on a boundary or on some subset. So if I have this here as a vibrating plate, okay, I'm sorry for the audience. So you have the vibrations, and you would be able to hold this here, but not on the entire plate. So this is true for almost everything. You can have distributed control in magnetohydrodynamics where you can apply magnetic fields and things like this. But in a mechanical thing, never. So for that matter, we talk about distributed controls to understand, and this is what you do all the time to understand how is this working, but one finally has to go to boundary controls or localized controls, right? This is much more meaningful. Okay, so yes, so let's go on with this. Now, we can set the P squared, the pressure squared is Y. And then from the second equation, you can see this identity. I can go back so that you can see this. So here is the Q. In any case, what this analysis shows you in a way or another, while this is being installed, this model goes down to the following. So I introduce a monotone a mapping, this thing here. Works? Is this the PDF or?
Oh, es ist super.
Okay. I might continue, and then we can look at the slides, go back maybe. So the point of interest here is that I can transform Euler's gas equation to an equation in terms of the pressure squared. And this equation I will talk about all the time here. This equation is this one. I maybe do an alpha here, minus ddx beta of beta p ddx of y is equal to maybe a distributed control. I told you this is not realistic, but I do this because that you can better see the relation to the previous lectures, right? This is the equation. And this is what we call a doubly nonlinear parabolic equation of p-type. P-type because of this. And if you look into this, if you resolve this, it is the standard alpha minus 2 y minus dxy to the power p minus 2 dxy is equal to u. You realize that this is what has come to be known as the P-Laplacian. This is the P-Laplacian. P-Laplacian. Interestingly enough, considering what also Rolf was talking about, the P-Laplacian you also get, by the way, if you minimize, there is a Ritz formulation for the P-Laplace. So you minimize 1 over p, integral over the boundary. You can do this in any dimension, of course, and here it would be just from 0 to 1 or something. And then you take, goodbye, and then you take this, right? And if you do the Euler-Lagrange of this, is the P-Laplace, right? And if you add, in the case that alpha is 2, this is a purely parabolic case then, because then this is identity. It's just the p-parabolic equation. Then, in fact, you can do this. So you add nu over, this is like a tracking type thing. Yeah? You add y minus y, deliberately, yn, if you wish, squared dx. And this is like a prox type optimization problem. And what it gives you is exactly the step that you have to compute if you do a backward Euler for the p-parabolic equation with alpha equal 2. You see, how do people prove existence, uniqueness, well-posedness of solutions for the p-parabolic problem? They do it using a backward Euler argument. And coming back to Rolf's talk, if you want to do domain decomposition, you could also think of a minimization problem. And the equation is coming out of a minimization problem for each time step then. And maybe there is a way to do it based on this. So now I hope that it doesn't die all the time. So the first paper that you see, and this is also a word to you, the students, right? You look. We are always looking for treasures, right? We are always looking for treasures in mathematics. Okay, we try the PDF. We try the PDF now. It's just not working. It did work when we checked Florence, right? It was nice. So maybe the title was too long. It doesn't.
Did you transfer a PDF on the computer or not?
We did not try. Maybe it's good, but if it does, I think it was also a problem with Adobe, right? If you look in this, but we can try, right? So I can fill the gap maybe. So if you think of this problem without domain decomposition, without any control, you would do a backward Euler here. So you would introduce a time stepping, and you would have a b alpha y at n plus 1 minus b alpha y at n over the time difference, right, minus the P-Laplacian at n plus 1, of course, and un plus 1. And you see, you put this on the other side, and you have precisely this kind of equation, which you can obtain using minimization also, right? Is this now the PDF?
Yes.
Okay, so we have a good chance to at least see some of the formula. Okay, good. I'm sorry for the inconvenience. So if you look into, and I said, you know, we're all looking for treasures. We look back to the literature, and I learned from you also, Martin, you very much like history, right? And it's always the difference between breadth first search or depth first search, right? And you have an argument, you want to know everything, right? But it doesn't work, right? So you need guidance in order to go to the literature and maybe to the root. Because in many cases, you know, right at the root, there are questions on the, you know, problems or properties that you do not see in the most recent literature. And this is true for Raviar. Okay, so here is, please don't read this. I mean, this, come on. If you do a PhD and start with your work, you would be intimidated by this kind of thing, right? But it is there. I mean, you can find it. It is there, and then you go and read and see, okay, subleved spaces, you know, you have dual spaces, and maybe Bezoff, and then the story is getting difficult. One thing that is missing here, and this is very particular for PDE control, is if you look into PDE literature, you most of the time do not find inhomogeneous boundary conditions. People like homogeneous boundary conditions, right? And in control, you need, not only that you need non-homogeneous boundary conditions, but you need very weak regularity, because if you heat something, you do a switch, you know, and we have seen bang-bang controls. I mean, you have L infinity or L2 controls, and most of the PDEs don't like this, and then you have to go to very weird spaces. So this is a difficulty that you always have if you do control theory, is the inhomogeneous boundary conditions. In any case, now let me embark, because time is running fast, on a bit of notation. I know this is not nice to read, but it is good to see at least, and I will explain you when I show you the equations. Is better than you know, reading off the complicated slide. But the point is incidence relation. The point is that we have multiple nodes that I call JM. Of course, I have a graph which is vertices and edges, and I have labels and so on. I have orientation, so I can say I have this orientation, and for that matter, I know where an edge starts and where it ends. This is described by this incidence to node matrix. Okay? Node to incidence, excuse me, node edge to node incidence matrix, right? Okay, so there is a lot of notation that you can use. Here is the object of desire, okay? Of my desire, maybe not of your desire, but this is the object, right? So you have the equation. This is the doubly nonlinear p-parabolic equation. Now you have continuity at multiple nodes. So here is the multiple node. The pressures should be continuous. You have this here is equivalent to the physical fact that the fluxes add up to zero. So it's like in mechanics would be forces add up to zero, right? And then you have out there, you have Dirichlet nodes, you have Neumann nodes that are under control, and you have initial data. So this is a network model, right? This is a network model. And if you have a bipartite graph, which means that you can separate the nodes into two classes, right? Then you can label the edges in such a way that in one set of nodes, x is always 0, in the other is always 1. If you do that, then you can reformulate such a system as a two-point boundary value problem for a system, right? Then you are back to classical mathematics, right? It's a two-point boundary value problem for a large system. Okay, so this is what we do, and there is Wellposedness has been looked at by a student of Herbert Egger and also others, so that you can safely say this Wellposedness is done. I will not show you all the spaces, so please. It's more important to see the relation to what Gabriele was talking about, and was maybe you have in mind the optimality systems that Stefan mentioned. So now we do control, and here we do running control, running of cost, and also final value cost. You see what just Arnaud Munch was talking about controllability. You want to achieve a profile at the final time. This would be, you talk about running cost. We also developed, in fact, a friend of mine back in Erlangen developed a concept of what we call nodal profile control. So in gas networks, here's the customer, and he wants or she wants gas at a particular flow rate and at a particular pressure. So it's a different question than what Arno was talking about, because you want to control at a particular node two variables, your two variables, pressure and flux, by boundary control. We call this nodal profile control or sidewise control. So all this is possible here, right? And then you have the cost function, and then you want to minimize the cost subject to y's and u's satisfying the network stuff, right? Now, another full slide, but not so difficult for you now because of the pre-knowledge that you have gained during this week. Here is the forward state equation. This already is the optimality condition implemented here. Here is the backward running heat equation. The backward running heat equation in a sense or another, because adjoint equations are always linear by definition. They're linear. But here you see difficulties, which I explain in a second. And here you have the standard tracking type, right-hand side for the parabolic problem. Again, continuity at the nodes. Continuity at the nodes of P is unfortunately now not the pressure, but the adjoint variable. But as we are living on, with the notation Y, we forgot about that P is the pressure. It's just the adjoint variable. And you have the same, you have the so-called Kirchhoff condition here. And you have somehow the Kirchhoff coming from the differentiation. I think Gabriele showed very nicely in the semi-linear context that you get always the derivative of the nonlinearity, at the current state times the adjoint, right? It's exactly the same thing here, right? And then you have the other conditions which are completely canonical if you do optimal control, right? One point one has to see here is a difficulty, and this is also the reason, the pedagogical reason, so to speak. You have a nice equation. If P is equal to 2 and alpha is equal to 2, this is just the heat equation. We know everything about that, right? We know how to do optimal control. We know how to do the domain decomposition, Benamou, Bruno Depré, and so on. But when you go a little bit apart from this, you don't, right? You don't know, right? But you would, of course, expect that you can somehow get similar or same results, right? And what is helpful here is, what is extremely important here, is not just a nonlinearity. It is a monotone. It's a monotone nonlinearity. So everything is monotone, and use the theory of monotone operators. This helps a lot, right? If you have anything, and then you are in the dark. Another point of caution that you may not directly see here. You see, P less than 2. Typically, the P here, in the P Laplacian business, P is between 1 and infinity. And P equal 2 is the standard theory. P less than 2 makes the system singular, because then the gradient is in the denominator. P bigger than 2 makes it degenerate, because then you multiply by a function of the gradient. So in flat regions, you have either degeneration or singular behavior. And this is reflected by the monotonicity properties a lot, right? So this is important. And the funny thing, this was in the slides that died, the funny thing is that here, in this case, P is equal 3/2. So it's less than 2. And this was done by Bamberger. And I know that you know Bamberger well, and it was Frédéric Nataf, I think. So very nice paper. And very nice because Bamberger was reading the paper, the dissertation of Stoner 3 years before, right? And then he realized, you need non-homogeneous boundary conditions, has regularity, developed regularity for that, and also considered already networks, right? Numerics is done by hand, obviously. I mean, there was, I don't know what machines they had in 1970, I know when I was a student, we computed on the Univac something with cards, with cards. So the plots are done by hand, right? But nice. Any case, so that was done by Bamberger. Okay, so this is the equation. And if you, there are now, of course, analysis what happens if you are flat. There is evidence that this cannot happen if you're close to an equilibrium of the gas network. The equilibria of gas networks are non-constant. And they are not, they're non-constant. And then you can show that, in fact, you don't have the flat region. Otherwise, you are in trouble because you cannot prove differentiability of the control to state map. This is, in fact, open in general, the general case. So if you deviate a little bit from the model, you're right in the middle of many, many new questions, right, that you can use. And this is at the level that you can do, also in a PhD. Okay, so optimality system. I will not get through, I'm sure, today. Now, time discretization is clear, right? I think you have seen this a lot. So you discretize in time, you get an optimal control problem that is now time discrete and continuous in space, right? So this is depicted here. So you have a cost that is discrete in time, but still is a sum over all the time instances, right? And you have this problem that is much more likely to be able to be suitable for domain decomposition with standard methods, right? There is a paper on because that's just the P Laplacian, right? There is a paper by Engström and Hansen. They do a Robin type non-overlapping domain decomposition for two domains, P bigger than 2. Nice paper. They use Dirichlet-Neumann or Dirichlet-Robin map and do this iteration as a nice proof also. So this can be done on this level. So if you start out with a project, you simplify, and then you have a tool to get started. And this, I think, is important in any thesis that you write, right? Okay, so this is a discrete time discrete optimal control problem. And with hindsight to Stefan, he knows well the instantaneous control that our friend Michael Hinze did a lot, right? I do this because, you see, the difficulty here is, even if you do time discretization, the discretization of the integral is always a sum over all time incidences, and therefore it's coupled. It couples all the time steps. And if you want to get rid of that, then you can do, you get rid of the sum and you get what is called instantaneous control. So you are left with just an elliptic, a nonlinear elliptic optimization problem, and you're right in the back to the lectures that you have seen, right? So, but it's not a simple and stupid simplification. It is what Bertzekas called moving domain or rolling horizon optimization, and this works in principle well close to equilibria, and this is precisely what you do in gas networks. Okay, this is the instantaneous control paradigm. So you have just a minimization over a static problem where you can do everything. Yes, I see this terrible slide of yours. 5 minutes. Okay, so let me say a few words, and I will not be able to finish here, and it's not important to finish here because it's more important that you understand where the problems are and what you do. So my point of view is, if I want to do a domain decomposition, I want to do it in such a way that was also mentioned, I think it was Felix who mentioned this, that if it's desirable to have a domain decomposition of the optimality system such that the decomposed system is itself an optimality system. And if you can do that, then you decompose optimization problems. Right? And this is nice because then you can use, for the subdomain problem, you can use standard optimization software, right? And I use IPOpt all the time, Kazadi, so that is a automatic differentiation tool also. So, okay. This is, for instance, one of the incidences. I have an initial condition on this, what we call diamond graph, and I have a boundary control. I would like to steer, oopsie, I would like to steer this particular edge to 1, right? And you can implement this with IP-opt and it does the job, right? The question now is, can you get this kind of thing using domain decomposition, right? And doing domain decomposition in space and possibly also in time, right? Okay, I think I have to speed up quite dramatically, so you can also do this for final value control, and so on and so forth. But the important point here in this meeting is domain decomposition. Why not taking very blindly, maybe, just the Pierre-Lyons type domain decomposition for this p-parabolic problem on the network. And what you see here is precisely the Lyons Ansatz, Pierre-Lyons Ansatz. What you see here is completely awkward, but it is exactly what you get if you have more than just one edge, right? If you can see that if D sub j, should say, not the DJ. If DJ is 2, then this breaks down to the standard Pierre-Lyons update, right? So it is. But I wanted to show you this because this reflects precisely the graph network, right? And you get this kind of domain decomposition, and you can use it and program it. In fact, I used the standard tool. You can use this. You can program this tonight if you wish. I can show you the code also. The PDPE code is available. Right? This is a completely nonlinear parabolic problem that is done by that. And you do 2 domains, and this is the interface that I plot over each other, so you don't see any difference. And this is the convergence of the traces and the Kirchhoff condition. In the case p is equal to 2, is a standard parabolic problem. And here's the same plot for p is equal to 3/2. So you see the convergence directly. Gabriela, I know there is no time, but you can now understand the following. If I do an optimality condition, right, I do the same thing. Right? I anticipate exactly the same thing, like what comes out of, in the very special case, one should say, by Depré is a very special case that you can transform the optimality condition into a Helmholtz equation. This, of course, is not possible in nonlinear context, right? But you get the idea from there. And then you would do the same as was done today, without the sigma maybe. So you have a Lyons type coupling at the interface, coupling between the state and the adjoint. And you have these guys here that are scattering operators that reflect the particular geometry of the network, right? And then you have to do the same thing for the adjoint equation, the same thing. So it's really the same kind of Pierre-Lyons type domain decomposition. And let me make one remark, which I like very much, and if you want to know more, this domain decomposition gives you an equivalent optimal control problem, which I call, together with the late Glowinski, and also Lyons did this, the virtual control problem. So this domain decomposition can be seen as equivalent to a virtual control problem where the virtual control is here. So you have the same, oopsie. I see. Okay. This is the chairman, the internal chairman, that just closes the section when time is gone up. This is Adobe. This is these. You know what I'm saying is you have the same cost function plus an additional cost function plus an additional term, and the additional term reflects the virtual control. May I try? Okay, no, this I don't want to do. I have no time, I know. No, here, maybe, no, this is, I still thank you for your attention anyway, already. So the virtual control problem is the same cost function, and you have to accommodate for, the control should accommodate to make this here small, in fact equal to 0. And this here is the classical Robin type boundary condition. This is the history from the previous iteration. This is the control that takes care such that the optimality condition writes down exactly the terms that have been on the previous slide. So you run this here, you can program this easily with IPOpt, and you obtain the convergencies here for a two-link problem, right? And I should stop here and hope that you understand the difficulties with the slides that I never actually occurred to me, but this is a keynote problem. So thank you very much.
Thank you very much, Günter, for the nice talk. Even with this problem, it was very, very nice, in my opinion. So.
I try to get over this.
Yeah.
Yeah.
Is there any question or remark from the audience? Laurence, please.
Oh, thank you. You are very brave. I wouldn't do the same. I wonder, this virtual control thing, is it something of domain decomposition as well? Or?
Yeah, I mean, this virtual control realizes, in fact, the interface, the matching at the interfaces. So you really, I mean, it's this. And you see this already in the very early papers of also J.L. Lyons and Pironneau and Pironneau. They have this. So J.L. Lyons and Pironneau, they did just a Lagrange relaxation. And this is more an augmented Lagrangian relaxation. But not for these kind of problems. I mean, if you take just the original problem and you write down the Britz-Ansatz and then you do an augmented Lagrangian with this, you get the Pierre Lyons algorithm out of that. And this is an Uzawa type saddle point iteration that was observed by Glowinski and Letalek, in fact. It's an Uzawa type. It's not very fast, therefore, right? But, you know, it's fine, as you could see. Thank you.
Any other question? So maybe I have one. I'm just curious. So you showed not this plot. There was another convergence plot.
Yeah.
But
this one
looked like
without control.
It looked like here. It looks on the right. Do I understand it correctly? So this is a kind of a quadratic convergence or superlinear convergence.
Yes. I cannot see this from the algorithm, of course not, right? I just observe, you know, this is the matter of numerical analysis. I just see it.
But here there is no domain decomposition in this, or
domain decomposition is two. I have two domains. I run this on two you know, here is x and here is t. I run the two p-parabolic problems here and here with the interface condition. And the iteration is the Lyons type iteration. Yeah.
Okay. Wow. So you get a domain decomposition method that converges quadratically.
This I don't claim, but it looks like, yeah. But I have no evidence, numerical evidence. I mean, numerical yes, but I don't have evidence on a theoretical level.
It's nice, in my opinion. Thanks. Any other question or comment? No. So if not, then we thank Günter again. Thank you.